So let me remind you, weekly assignments in 4 weeks, final projects in 5 weeks. Uh, every day is going to matter. You need to plan your time very carefully. And that's really what today is all about. So next week is wild card, where everybody does something different. After that, we're done technical content. This week we started in the last few years, it's on integrating a system. And the reason we did it is we would be sad at many final projects that weren't really integrated. And so I'll show you, this set the record for the worst Fab Academy project ever. A student actually submitted this as their final project. And it's sort of a masterpiece of, it's clearly cobbled together. It would fall apart if you shake it. That's not a system. So compared to that, the featured assignment was a scoreboard for sports. Yeah, I actually, yeah, that student, yeah, we had a lot of trouble. I don't recall if that student even finished or not. This was a scoreboard, and just what I wanted to show you was on this page, they go through the modules, the components, and then here are the wiring harnesses without a tangle of wires, and then everything comes together in the scoreboard. This isn't a heroic project. It's a scoreboard, but notice just it's designed as a system, how everything comes together so well. So this is a nicely integrated project. The one I showed you is a poorly integrated project. This week's assignment is design and document the system integration for your final project. So to do this week's assignment, and in fact, let me go back to reopen the issue to explain that part. Let's go back to here, schedule issue. So to do this week's assignment, you need to settle the final project. And what we want, and we saw an example before the break of, we want to know all the sub-elements, and we want a design of how they're all going to come together. Next week, we're going to open up signups for the final project presentation. And to sign up for the final project presentation, you need to have this assignment submitted where you have the design of the system. So you still have 4 weeks to finish the system, but after this week, you've settled what the project is and you've designed the system. So this isn't a single skill like 3D printing. This is a tour through many aspects of designing systems, making systems, testing, and a lot of today's class is going to be about failure. I'm going to talk a lot about all of the ways systems can fail. So first, a bit about design. So this is a history of design at Apple. At the beginning of the computer era, there were IBM PCs and Apple Macs. IBM ended up selling off its PC business. it gave up. It sold off the PC business, and IBM has struggled ever since. Apple has become, for many years, the world's most valuable company. The IBM PC was a box. You had some circuit boards, and so you made a box for the circuit boards. Apple embraced design. They made beautiful things. And one company became the world's most valuable company. One company gave up on the business entirely. So it makes me sad when a final project is just a rectangular laser cut box with a finger joint. So, as you work on your project, do you want to end up as IBM selling a commodity rectangular box? Or do you want to end up as Apple becoming the world's most valuable company? And the difference is design. And so design may seem soft and intangible, and it can have huge impacts. So first of all, this was a class colleagues did as an experiment at MIT on, instead of how to make anything, it's how to design almost anything. Broadly, design studies go way beyond the class, but just a few comments about it. So one is terms in design are similar to spiral development. Conceptual design is thinking about what you want to do. Preliminary design is roughing it out. And then detailed design is exactly that. It's filling in the details. But you don't want to do detailed design too early. You want to pass through these stages to refine the design before you fill in the details. This is a recitation done by a Fab Lab guru that's a nice tour through the subject of how to make designs usable. And he talks about a number of basic principles of design. It should be easy to figure out what it does. He has this great example of there's this button and it can go either direction, and it's just not apparent what the button does and what does it mean. You want mappings to map onto the physical action. You want to avoid modes, so you need what state the system is in. Are just some general principles of good design. This was a topic just on usability, and there are a number of versions of principles for, these are a bunch of different versions of principles for what make good interfaces. And again, these sound obvious, but each of you have struggled with systems that violate these basic principles. So these are just some pointers for principles of good design. Then DFM is design for manufacturing. And here the class you're taking will help you with that, in that there's a huge difference between design by somebody who's just sitting at a computer and design with somebody who's familiar with the process of fabrication. So you don't want to design just what you think, you want to design around the process to make it. So one is trying to use a small standard set of components. Net shape is you want to minimize processing. So for example, 3D printing done well is net shape. You make the final shape in one go. Typically manufacturing, there's some post-processing, but you want to try to minimize waste in the process. Fasteners are generally considered something to avoid wherever possible because they add labor and they can walk. Adhesives, generally you try to avoid because you can't undo them. Where possible, flexures are really good because flexures don't need fasteners, they're self-aligning, and you can disassemble. An example of self-aligning features was I had showed in the machine building of rather than having tolerances to align things, this is designing so that the features self-align when you build it. One common principle is minimizing the number of components. So Tesla, and this involves a colleague who I work with closely at MIT, has done large-scale casting to make one interesting part that can replace lots of separate parts. This is the reason I'm showing this is Formlabs did this competition between fast 3D printing and injection molding. And they're a bit biased, of course, but showing that a farm of fast 3D printers can beat an injection molder for a reasonable sized run. And so as part of DFM is picking the process you're going to use to make it and then designing around the constraints about that process. And the design for example, for 3D printing, you need to get the resin out of it. For injection molding, you need the runner to get the melted plastic into it. And so you want the stages in the design process to propagate all the way back in the fabrication process to propagate all the way back into the design process. Then the class has stressed documentation every step of the way. Documentation is essential in the transition for manufacturing. There are a number of tools helping. So this, for example, is a nice BOM tool for KiCad that will export your parts for manufacturing. This is a really nice tool that comes out of a group at a Fab Lab in Hamburg with collaborators that aims to automate documentation. And so you do the design and it automates producing the documentation for it. And then part of the documentation is how to use it. How-Toons was a project started by former students that make these really great cartoons to teach you how to do things. And again, the manual can be boring and tedious, or you can add value in explaining how to use it. And so these are all steps in documenting your work. So please don't finish this class with a rectangular box with laser cut finger joints and that it. Think about packaging that's interesting to interact with, design of a system that's interesting to interact with, that's satisfying for the ergonomics. Yeah, and I'll absolutely, that's a nice comment. Let me go back to one of the gods of what I'm talking about here is Don Norman. And this is a fabulous book about about the design of everything. The cover is a teapot that pours on your wrist. And it's a beautiful tour through good and bad design of everyday things. I'll add a link to that. Okay, so just some general thoughts about good versus bad design. It may sound soft and intangible, and it's the difference in the fate of Apple versus IBM. Then comes packaging. So if we look at this project, one thing that's wrong is circuit boards can't be just dropped in a box. They'll fail if you jiggle them. You need to mount the electronics. Let me add a link to so in this project you'll see this design of the wiring harness. So rather than a tangle of wires, they designed the wiring to connect all the parts. Here's why that matters. Uh, um, when the A Airbus A380 was made, they made a mistake in the wiring, and it ended up being $1 billion problem uh, uh, for the getting the wiring wrong. And so uh, one of the most common failure modes, and I'm going to talk a lot about failure modes, has to do with wiring. And so once you have a physical design, once you have the components placed, part of the design is the wiring routing. It's easy to neglect that as a detail at the end. In the Airbus case, it cost $1 billion to fix a mistake in it. You have to design the wiring. The reason I have this linked is when you assemble the system, there might be slight misalignment. And so this is Prusa explaining when you assemble the 3D printer, crucially, there's degrees of freedom to micro adjust to tension the wires. And so, in this housing, there's a little bit of degree of freedom to rotate the housing to take up slight misalignment when you fabricate it. And so you want to think about the error budget for the system and having enough degrees of freedom so that you can take up slight misalignment when you make it. Here, so in molding and casting, when we talked about molding with printing, this was an example of taking an ordinary FDM print, but just doing a really good job with finishing it. And so here they're making beautiful molds from it. And they started with just the FDM print and then post-processed it to make this beautiful surface finish. One more thing that makes me sad is when like you have rough machining, when you have crude 3D printing, beautiful objects are nice to look at and they feel good to touch. And so don't neglect the surface finish at the end of the project. Okay. So part of this week's is in designing and documenting the system integration is we're going to look for all of these things of where does the electronics go? How is the wiring routed? How do you align and assemble the system? Then comes testing. So almost everything you make will fail sooner or later. You want to fail while you're developing and testing it. You don't want to fail after you send it out into the world. So quality assurance is preventing defects in the first place. Quality control is finding defects and fixing them. And testing is identifying the defects. So first of all, one of the best ways to test a system is to shake it. If you shake it or drop it, does it keep working? Burn-in testing is leave the system running. So for example, one kind of failure mode in software is a memory leak. And so everything runs fine, but if you leave the system running for a few days, you're slowly leaking memory and it grinds to a halt. If you make a motor controller, it may work fine when you move the motor, but you're overheating. And if you run it for a few hours, you burn out the transistors. So just run the system for a while. Cycling, turning everything on and off a lot of times stresses the system. Often there's power transients, there's mechanical loads. So turn your system on and off a lot of times. Environmental testing is, does it work when it's hot? Does it work when it's cold? Does it work when it's humid? There's all sorts of failure modes for that. Fuzzing is an interesting kind of testing. Fuzzing is you spray random junk for the input to your system. And it's a common way to test for vulnerabilities is you just give it nonsense and you see how the system responds to it. And you can uncover a lot of, for example, security vulnerabilities by fuzz testing. Okay, so now I'm going to spend a while talking about how systems fail. So first is if you look at stress versus strain. Remember, stress sounds like press, pain sounds like strain sounds like pain. So you apply stress and the system responds. There's a linear range where you're pushing and it's elastically deforming. This is fine. There's a nonlinear range that's usually okay. There's a range where you get into what's called plastic flow, where it becomes hysteretic. And so if you push on the system, it doesn't come back to the same place. That's bad, you're deforming it. And then eventually you get to the strength limit where it fails. So you want to make sure loads are always within the elastic limit. I've linked this just because this is a paper on a project we did on multiphysics modeling. And in this, we cover how to model failure. So here's a test part. And when you start opening it up, there's a stress concentration. And then you'll see the crack appears there and it propagates. So when a system fails, it fails where the stress is concentrated. And a very common form of that, in fact, I just did this weekend. I failed to do what I'm about to describe for you. I needed to make a flexural clip that fit into a pipe. And so I had designed the shape of the flexural clip. And then I just put it on a base like that. And it snapped right there. And the distinction is if I blow that up, I had a sharp corner where it failed. And instead, in the second version that works, I have a fillet like this. So it's coming in and I have a fillet like that. And so the difference is that's a sharp corner. Here I've filleted the corner. At the sharp corner, a crack initiates and propagates. When you fillet the corner, it's hard for the crack to initiate. So just simply filleting corners has a huge difference. I'm just following along with the chat. Filleting the corners makes a huge difference in the likelihood of failure edit. Then this is a review of the original MakerBot replicator. Bree Pettis describes it as on-the-job training. He did a lot of things wrong, and the most important thing he did wrong was this nice laser cut wood looks great, but in that design, he's nicely designed a shape like that in the wood, and then the threaded rod comes in, and then he has a nut here. The problem is this is wood, and if you go back to this range of plastic deformation, when you tighten the nut, it's very slightly deforming the wood. The wood is plastically deforming. It doesn't come back to the same place again. And so you could assemble the MakerBot, get everything working, and then in a few weeks, it's no longer printing well because everything is drifting and moving. So preventing fasteners from moving their position if you're using fasteners is essential. And so that's where you want to have thread locks, lock washers, lock nuts, things that prevent fasteners from moving. One more problem with threads is you can strip them. If we go to the snap machine, let's see if I can. So there's a few versions here in these pictures. This was the first version. And Nadia and Jonathan are good at what they do. They made it. They inspired lots of people. Multiple people tried to make it, and they all had trouble getting it to work. And the problem was right where my mouse is right now. So in their design, you have the threaded rod. You had the guide rails, and then they were mounted. The problem was if your milling machine isn't perfectly square, the guide rails can be very slightly misaligned. I'm exaggerating. If the guide rails aren't exactly parallel, then when you try to move the stage, it'll bind and it doesn't move. And so they made the machine on a perfectly squared mill, but somebody making it on a sloppy mill, the rails weren't perfectly aligned, and you couldn't reproduce it. The fix is almost easy to miss. And so in the picture there, all they did was instead of having the rail come out into the end piece, the rail comes out, and then let's see. This then is the end piece. They have a little flexure, and that flexure gives just a little bit of elastic motion. So in the machine, position along the thread is sensitive, but a small lateral motion about the rail isn't sensitive. And so if you add just a little flexural degree of freedom on the rail mounting, then if they're not exactly right, they can just move a little bit relative to each other. And that went from a machine that's very difficult to make to a machine that's much easier to make. Then this is an extreme form of, let's see, it's if you're new to it, Tacoma Narrows. Bridge failure. This was a really dramatic event. So this was a bridge, in the 1940s that collapsed. And okay, so it's a bridge you drive cars over, and it looks like it's made out of putty. And so it started this incredible swaying, and eventually collapsed. I mean, this is a rigid road. And so what failed there was not a static, but a dynamic instability. So, I described stress strain. And so they had designed the bridge so it could withstand the loads of the cars and the deck of the bridge. But what they didn't think about was the dynamics. And so it was windy. The wind would come off the guy lines holding the bridge, and they would whistle. They would in the wind they would whistle, and they would vibrate back and forth, sort of like a musical instrument. The musical the vibrating guy lines would then connect to the bridge surface, and there was a resonance like pushing a swing, and at just the right frequency you could vibrate the lines, and then the road surface would vibrate just a little bit, but each time around it would put more and more energy in, and it just kept building up until the bridge fell down. And so you couldn't find the failure running statically. You only found it when it was dynamically. And another version of that is chatter. In a machine tool, a common problem in machine tools is the machine tool is stiff. It can do a good job, but when you start machining faster, you get chatter in the tool, which is a dynamic rather than a static problem. So you need to study the dynamic loads on the system, not just the static loads. And there's a lot of failures that happen from that. Okay, so that's just mechanical failure. Then comes wiring. So one kind of failure mode is the copper traces on the circuit board are glued down. You take copper, you heat it, squish it, and glue it. You don't have to pull that hard to rip up the traces. So a sad thing is you design a circuit board, it's working, you bring it to the lab and it's not working. And what happened is there was, for example, too much force on a connector. And as you pushed on the connector, it ripped traces up off the PCB. It's not quite as much of a problem on board house PCBs, but you can still rip up those traces. A variant of that is you have connectors going into the PCB, and you pull on a wire and it pulls out of the connector. And so strain. Oh yeah, let's see. I'm just linking to these are strain reliefs for wiring. Anytime something goes in and out of electronics, you want to plan what happens when there's a load on it. And you don't want it to rip up the traces. You don't want it to pull out of the connector. You want something to mechanically handle the load on the connector. Connectors ideally are polarized. Oh, and in fact, let me add a note on that. When you might have a wiring harness. I'll give you an example that I did recently. I had a wiring harness that had ground, power, transmit, and receive. And all of that went to a board, and then that went to another board. And there was an in and an outside. If you connect it backwards, in this case, you're connecting the 5 volts accidentally to the transmit. And what that did was on the board, it went to a microcontroller, and then the board was running at 3 volts. And connecting, this was the transmitter that talks out, but connecting 5 volts into the transmitter on the 3 volt process actually went through the processor and it killed the regulator. So one way to avoid that is connectors that are polarized, so you can only connect them one way. And another common thing you'll see is if you have a transmitter and a receiver, say, GPIO pins, coming off of the board, you'll have a 100 ohm resistor. And the 100 ohm resistor is small enough that it doesn't limit how fast you can send data, but it's big enough that if you misconnect, so you're trying to put voltage into the output, it serves as a current limiter. And so just that 100, so in fact, the problem I described, I fixed by putting in a 100 ohm resistor to protect the circuit. This plane crashed, everybody died from a fire, and it had to do with wiring insulation. So in the power output device class, I talked about kilovolt per millimeter, and less than that for smaller gaps is dielectric breakdown. Wiring insulation can abrade if you rub it, and can break down with voltage on it. And it turns out that Kapton was being used, and it was flammable, and it caused the fire that led the plane crash. So Jacob is asking about the 100 ohm resistor. Jacob, I don't do them automatically every time. I do them where there's a chance to misconnect it. And I don't do it, for example, if I'm just making something for myself, but what I described was used in a collaboration with a global company sending parts all around the world. And so the 100 ohm is if there's a chance of misconnection, and if you need to worry about users outside of your supervision. And so, just wiring breakdown can bring down an airplane. Here, what I'm showing is this was a machine my student Jake made. Here, he's making a nice wiring guide. There, the way he does it is he just simply takes a tape measure, a metal tape measure, and puts it in a sleeve, and that provides the wiring guide. Oh yeah, and actually, I've got this linked here. This is the $1 billion. Then connectors corrode with time. One way, let's see, I'm going to add a note. So connectors can corrode, and it depends in part on how much you spend on the connector. For example, whether you have gold on the connector. And so when connectors corrode over time, the joint, and this can be worse in humid or salty places, the joint can eventually fail. And so the note I just made is one of the things I check when a system fails is you just take everything apart and put it back together again. And that can be a test for connector corrosion. And let's see, I already talked about insulation. Okay, so that's wiring failures. Then many kinds of electrical component failures. So once you're doing power electronics, it's very common to burn out your power transistors. So in a nice H-bridge, so if we go to output devices, so in a part like this, it's got this really nice module here, and you'll see it's looking, are you asking for too much current? Do you have not enough voltage? Is it overheating? If it does that, it'll turn everything off. And so if you're using it as a motor controller, the motor will stutter, and the stutter tells you it's protecting you from killing it. If you're just making your own transistor circuits, they'll die. You'll blow out the transistors. And then a big one is inductive flyback. So remember, a motor looks like a coil. It's got a magnetic field going through it. If we then go through a power transistor, conceptually, when you open a switch, so we've got the current flowing. When the current stops, in effect, it tries to keep it going. The magnetic field quenches, and you get a big voltage and current spike. You can get kilovolts. And that voltage spike can easily punch through your power transistor. And so a common solution for that is to have a diode. Current should always go in the foreground direction, but you have a reverse protection diode that normally does nothing, but it prevents current going in the wrong direction. If you connect, so in the example I just described, if you connect 5 volts to a 3-volt processor, you'll kill it. I'll add a little more detail. By current limiting, what I meant there was things like the 100 ohm resistor that prevents you from shorting. These are parts whose job is to specifically switch quickly for high voltages to protect your circuit. And then EMI shielding matters for things like sensors and radios. And so this is an article about we're surrounded by 50 or 60 cycle magnetic fields from power lines. Guitar pickups will pick that up and you'll hear an annoying hum. And so this is an extended study on how you make shields to protect against EMI by making electric and magnetic shielding. Okay, so those are common ways components fail. And let's see. I'll add one more. So the voltage regulators we use have an input and an output. And so you connect power to the input, and then you get power out to your circuit. Generally, Sahin is noting on the shells have a little box around them, and that little box is EMI shielding. That the reason shells that's a nice example. The reason shells look like the way they do is this little box is an EMI package that completely seals the electronics. The regulator, if you put power the wrong way, if you try to power the output rather than the input, typically that kills the regulator. And so one way to do that is with protection diodes. So the diode makes current only go one way, and you can't run the regulator the wrong way. Then power failure. So you need to design the power budget of how much current and voltage you're going to need. You need to make sure your supply can do it. So a power supply acts like an ideal battery with a resistor in series. This resistor is the compliance. And what it means is as you pull more current, the voltage droops. And so you need to make sure your power supply has enough compliance. So when you're pulling full current, you're still getting the voltage when you test at a lower voltage. Batteries, the voltage drops, batteries have a lifetime. I've had projects fail when when it seems like there's a software bug, and all that's happened is there's a battery whose voltage is dropping, and so the processor is running marginally. This was at a Fab Academy boot camp. We had a disaster because connectors weren't clearly labeled, and in putting the system together for this nice milling machine, one of the instructors, who will go unnamed, connected a 48-volt supply to a 24-volt input and blew up the system. A really tricky power issue is, so you have your power supply, 5 volts, 3 volts, you have ground. In between them is, say, this is your processor. And then over here, say, we have a motor in an H bridge with power electronics driving it, connected. Everything's running fine. The processor sends a signal to the H bridge. The motor switches. But if you look at the volts versus time on the power rail, instead of being a smooth curve, it looks like that every time the motor switches. And if these spikes get big enough, they can do what are called brownouts, where they force the processor to reset. And then this is really tough to debug because when you're running, it looks like you're getting software errors. And the software errors is because your processor keeps resetting itself. But what's happening is the motor switching is creating transients on the power line that are coupling into the software. And so to prevent that, one way you prevent it is having inductors in the power line. One of the main ways you prevent it is having big capacitors for bypass. So a common cause of that is you don't have big, let's see, I think I have an example of that. Output devices. So on, yeah, like on this H-bridge example, the first version I didn't put enough bypass on it and had all sorts of issues. And so I ended up putting just a much bigger bypass capacitor. Then wiring, a wire has resistance and it has inductance. The inductance limits how quickly you can ramp it, and the resistance, remember, power is I squared R, and that's heat and that's dissipation. In fact, Hank, can you put in the chat the page for the study somebody in your lab recently did? Somebody at the VOG looked at their specs for how skinny a wire can be and how much current it can handle. And so VOG did a test on failing wires by pulling too much current through them. And then, yeah, this last one is, once you have more current, grounding, how you ground really matters. So so a minute ago, I drew this. This was power, this was ground, and I described some things connected in this. let's see, copy. So this was a test at the VOG. I'll link this, where they made skinnier wires, pulled a lot of current, and then they watched to see how they failed. So what I just drew here is a terrible idea. And here's why. What you want to do is, if this is your supply, now this matters for high current, not for low current. The reason what I drew here is a terrible idea is, remember, there's some resistance in the wires. And so if you do it like this, if this device is pulling a lot of current, it means the voltage on this device is going up and down. So what you want to do is you want to have what's called the ground mecha, and you want to bring power to your devices, and then you want to route them to the ground. Conceptually, these are the same thing. The power goes there. But remember, each wire is a resistor and an inductor. And so at low voltage and low current, and if you just trace the wires, these two are the same thing. But when you're pulling a lot of current, now if this pulls current, it doesn't mess with the ground for this one over here. So for low noise or high current, you want to route all of your grounds to one place. And so if you ever hear a hum on a microphone, on an audio system, that's an example of getting that wrong. That's called the ground loop. Okay, next comes how your software fails. So I mentioned memory leaks. So if you allocate variables and then let's see, Jacob is asking on a ground plane. Ground planes are for a slightly different reason. Yeah, ground planes help a bit. So a ground plane, so a 2-layer PCB is you route traces on the top, traces on the bottom. A common 4-layer PCB has traces on the top, traces on the bottom, and then you have an internal ground layer and a voltage layer. This whole plane, so you have a whole plane of ground in the circuit board. The ground plane reduces the resistance. So if you pull current, it reduces it. It helps distribute it, and it helps shield. That helps on a circuit board. Generally, in what I'm describing here, this isn't on a circuit board. Here, what I'm describing are multiple different components in a system, like a 3D printer controller. Okay, so many software environments will let you write bad software where you allocate memory. You may not even be aware you're doing it, and you don't reclaim it, and eventually you run out of memory. More recent languages like Rust prevent you from doing it, but C or Python let you leak memory. This is an explanation. I had mentioned Heartbleed in the security class. This broke the internet for a while. It was one of the most serious security failures in the internet. And it was a buffer overflow. And again, Rust won't let you do this, but in C or Python, you can have a buffer allocated, but then you can try to read or write beyond the buffer. And that lets you access things that you're not supposed to see. And so that can go from bugs to software attacks. Again, Rust won't let you do this. C will. A race condition is you can, for example, spawn threads in C. Each thread does a task, but unless you synchronize them, the output of your program depends on which task finishes before the other. And those can be really tricky to debug because it can depend on the operating system scheduling. variable scope is nasty, where in a program you have modules, and if you have a global scope, you can have a variable here that interacts with a variable in a way you don't expect down here that happens to have the same name or uses it for a different purpose. So generally, you want a scope to limit variables to keep them local so that they can interface globally. I had mentioned again in the security week that you may think you're writing good stuff, but like last week in application programming, I covered a bunch of different libraries you can use. Those libraries can introduce dependencies. You write good, careful, secure code, but a package you pull in can be vulnerable. And so there's a big package of issues around just vulnerability from your dependency. And then a common historical lesson is the failure of security through obscurity. Security through obscurity is you try to make a system reliable by making things secret. And the problem is clever people can generally find what's wrong with what you're doing. So the opposite of security through obscurity is to have completely explain how your system works, and then you identify pieces of secret information. So like here, I'll grab, these are some cryptographic tokens. This one is for a supercomputer. This is for some cloud services. The way these systems work is completely open. Everybody can understand how they work. But to access them, you need a key, and the key is stored in this physical device. And so you can completely learn how it works. The protection comes from I have this physical device. Yeah, Ricardo is making another note. C lets you make pointers, and so you can pass pointers that can do almost anything, and they can let you destroy things if the pointer isn't pointing where you think the pointer is pointing, as opposed to passing values. Oh, and sorry, another comment from the I'll add in the I'm jumping back briefly from a comment in the chat on the grounding discussion. We had a problem in my lab at MIT. We had a 10-foot shop bot. We had the computer running the shop bot, and we kept getting glitches, weird issues. And so we just got a really fat metal braid, like a 1-inch strap. And we simply took the ground on the ShopBot controller, and we took the ground on the power outlet at the computer, and we put a really fat ground between them. And then everything started working. And what was happening is the ShopBot was plugged into building power, the computer was plugged into building power, but the building ground wasn't a good enough connection. And so the voltage was changing between them. And we put this fat strap and we grounded them better to each other, and then it started working. Scaling is, so this is a link to the math class I teach. And a lot of that class has to do with the order. The order of an algorithm is how many steps does it take versus how large is the problem. And just a good algorithm is order n. A terrible one is exponential e to the n. N squared algorithms often are borderline. N log n is more efficient. All of this shows up in scaling. So if you take the magic cards and you want to recognize the cards, and you have an image recognition system, it might work for 10 cards, but it becomes unusable for 1,000 cards. And you won't see that in small testing. You need to understand how it behaves as it gets bigger. And in fact, this is a beautiful article from a colleague in my lab. You can actually have like, water boils, ice freezes are phase transitions. You can actually have phase transitions in the complexity of a problem. So testing as you go from small to big can lead to very different behavior. It's not at all straightforward that if you add more cards to the system, there'll be a linear change in how well the system works. Manufacturing. So during COVID, car factories shut down, and they shut down in part for $1 motor controllers. So it turns out to make the car work, they can have 100 motors in a car. Each motor needs a motor controller. The motor controllers are made from chip fabs that are a few generations old. And the car companies hadn't appreciated that without the $1 motor controller, their whole business grinds to a halt. And so COVID and now the fights over tariffs lead to a recognition that everything can be working great and your supply chain can fail. And a variant of that I had mentioned is integrated circuits. In fact, I should mention that. There's a boom bust cycle for integrated circuits where a part you want isn't yet available because they're just making it, but it's great. Then you start designing around it. Then they make a lot of them, but eventually their sales fall off, so they stop making them. Meanwhile, you're using a lot of them and suddenly find you can't get the part that you need essentially. So supply chains introduce all sorts of vulnerabilities. Right now, there's a lot of attempts to getting control over that. And Fab Labs are really relevant to that, Fab Labs are, let's see, MIT News, Fab Lab. This was an article MIT did on how, this was a nice example. Fab Labs are helping bring back manufacturing, one lab at a time rather than through big factories. Okay, and yeah, this next link is this was an article on exactly what I was describing on this boom bust cycle of chips, and I can't tell you how frustrating it is to have a fabulous thing designed, everything is working great, and then a chip that's at the heart of everything becomes unavailable. And it's guaranteed to happen. And so you should be paranoid about like having supplies of parts you need, keeping track on them, keeping an eye on replacement parts if they're not available. Stephen has an example. NASA had to buy parts on eBay. I hadn't heard that story. Oh, look at that. That's a great example. 8086 is the original IBM PC processor. This is a really interesting failure example. The Mars Climate Orbiter, $100 million project, years of development, 10 months to travel to Mars. Everything was going great. It got to Mars and it burned up. Believe it or not, it came down simply to there were two different teams using it, and it was just simply units. Um, there was a conversion between English units one was using, metrics units another was using. They didn't notice that, and so a message went from one to the other. They were using different units, and they made the spacecraft do something crazy, and simply the unit conversion um, uh, led to the failure. Uh, the then it's important to fail. So this has been one of the worst examples of when I described early in the class, I described starting at the beginning and going to the end versus working in bigger and bigger spirals. Boeing's Starliner is a $1 billion project, and they finally flew it once, and then they flew it again, and that failed, and it's going to be canceled soon. It's an extreme form of trying to get everything, spending billions of dollars, and then seeing if it works. SpaceX, noting some controversy around SpaceX, has done a good job of just rapid iteration, and they test a lot and they fail a lot. And I'll add a link here to, I gave a talk about this. This was a MIT TEDx talk I did. Let's see, why is that not working? Okay, so I'll add a link to this talk. Let's see. Yeah, let's not. This is probably a better link to it. This was about ready, fire, aim, where I talk about how many things in my lab come from failure, but beyond just failing, you need to do your homework. Then you need to fail. Then you need to learn from the Then you need to learn from the failure. And so that's a whole talk I gave about that. So then, let's see, more notes. After you've done everything I described, you then have a system. It's great, everything is working, and then next week you find out it's failed. So then you need to fix it. So one good way to fix things, surprisingly, is if you drop it or shake it or disconnect it and reconnect it. That's just simply testing, are there like connectors oxidizing? Are there loose joints? And so ultimately, if that fixes it, you need to do better and you need to find where they are to prevent it in the future. But just you know, disassembling and assembling everything is a surprisingly good way to fix things. Modularity is a really important principle. Let's see, Hank, what is this for?
It's to figure out the topic.
Let's see the. Okay. Oh, it's just to that. Sorry. Okay. Modularity is, remember I talked about in networking week, breaking your system into a lot of separate modules. Modularity lets you test each part separately. So again, like just for motor control, if we go to mechanical machine design, and then, if you take one of the, so if this fails, there's not much you can do. But if you make a modular, a single motor controller module, if you make a processor module, if you make a COM module, if something fails, you can take parts apart, you can test them separately, and assemble them back together again. And so you're both mechanically and electronically and code. If you have one big program, you can't test it. It's generally a good principle to have lots of parts you can take apart. And again, I mentioned this before, I'll mention again, to debug, you can debug from the top down by taking parts out of the system, or you can debug from the bottom up by adding parts into the system. This is an amusing note about an amusing person. Widlerizing is the name for enthusiastically destroying something that breaks. Let's see. And that doesn't help debug the system, but it helps you. Ilmenau is asking a connector about a question about connectors. So that's a tricky question. Connectors are good because they give you modularity and let you separate parts of the system. Bob Moog's pioneering synthesizer company eventually failed because he had put chips in a socket to make it easy to change them. But when he shipped them, they would come out of the socket, and it made the systems unreliable. And that's one of the reasons the company failed. So the question, Ilmenau, is really tricky. The connectors help you with modularity, and then they can also introduce vulnerability. And it comes down to if you never ever need to take it apart in the life of the system, it's a vulnerability. If you need to take it apart to debug it and fix it and improve it, it's also a vulnerability. It's a very tricky question. Then some life cycle. So there's emerging rules, and Europe has been a leader on right to repair, on making systems accessible to fix them. Increasingly, and again, Europe has been a leader, increasingly manufacturers need to be responsible for the end of life of products. And so it's important to look ahead to, at the end of life, how do you disassemble it? What can you reuse? What can you recycle? And increasingly, that's going to be required, not optional, to plan the whole end of life. So I should have left this open. I'll come back again and wrap up with this issue. This week's assignment is design and document the system integration for your final project. So during the random review, the dog on the trash can, we saw a nice example that was half of this assignment. We saw all the electronic modules and how they'll be connected. We didn't yet see CAD for how everything will fit together. After this week, now you need to settle the final project. You need to design how all the parts are going to come together. You need to document all the parts in the system for this week's assignment. And then if we come back to here, signups for the final exam will open up next week, and they'll be based on this week, meaning this week is where you show that you're going to expect to be ready for the final presentations. And then we start this 4-week push on the weekly assignments and 5-week push to the final. So, questions or comments? After this week, again, you should have CAD for the whole final project. You should have system diagrams of all the parts. And you should have the schedule for completion. And as you work through this, just think about, do you want to be Apple or do you want to be IBM? Do you want to design something beautiful or do you want to make something that's a commodity as the challenge for this week? Okay, so you have this great open time Saturday. Not enough people come to that. You've got unlimited hot and cold running help on Saturdays. Then come to All In and learn about how to have impact for Monday recitation. And I'll see you next week. Wildcard week will be, wildcard week is dangerous because it's too much fun. It'll easily distract you from everything else you need to do because there's so much fun to do that week. So that's a good problem you'll have next week. Okay, happy system integration, and I'll see you for the recitation and class next week. Bye-bye.
Bye.
Thank you
Thank
so
you.
much.
Bye-bye. おやすみなさい。
Bye-bye.
Bye.
Bye.
Thank you, Dad.